Okay. Welcome to today's webinar. I'm Matt Cederberg, Chief Strategy Officer at Coreform, and I'm the host of today's webinar. Will be given by Dr. Steve Owen from Sandia National Laboratories. This is the second of two webinars that we're giving to introduce the new machine learning capability that was released in Coreform Cubit 2023.8. And this one is on part classification and reduction. So the agenda of today's webinar, Dr. Owen will present this. First, we'll just introduce Coreform Cubit to you if you're not familiar with that software. Then Steve will talk about what part classification and reduction are, and then how to use the new Coreform Cubit machine learning tools to automate those processes. Then he'll touch on how to leverage this capability to create your own training data, to identify your own parts, and then touch a little bit on how to leverage all of this with Python scripting. If you missed the last webinar that was on using machine learning for defeaturing, then you can view that recording at coreform.com. So just to briefly introduce Coreform Cubit before I pass it over to Steve. So Coreform Cubit is used across many industries for advanced meshing for challenging simulations. It's often used if you have a standard finite element analysis or computational fluid dynamics pipeline, but you have meshes that are just more difficult to mesh, especially hex mesh. It's used to do that. Or also if you have a solver that doesn't have its own preprocessor or mesher, Cubit's often used in those situations as well. Its strengths are its ability to import CAD data, native CAD data directly, clean that up. We have a strong suite of semi-automated and automated hex meshing capabilities. And Cubit's often used in automated processes with our Python and scripting integration. And then today, Dr. Owen will introduce the new machine learning capabilities. So this webinar is being recorded, and please feel free to type in questions throughout the webinar and we'll answer them. And introduce Dr. Steve Owen. So Steve Owen has been a developer for Sandia Cubit for several decades. He's the lead on this machine learning capability, and he also authored the excellent 2-day Cubit training materials. And so with that, I'll turn the time over to Steve.
Thanks, Matt. Are you seeing my screen here? Do I need to share it?
Yeah, I see it perfectly. Yep.
You're okay? Okay. So as Matt mentioned, we started with some initial work that we did with machine learning. Over the past few years at Sandia, with our sort of design through simulation tools, we've really been looking at how we can utilize some of the new machine learning technologies to really speed up the process of really design to analysis. And we've targeted specific areas that we want to particularly look at. The first one we looked at was, can we use machine learning to help us do the defeaturing process? And that is, can we predict particular regions of a model that are going to cause us problems, and can we use the tools in Cubit to help us resolve those issues prior to meshing? What we want to focus on in this webinar is to look at this idea of part classification and reduction. So the idea there is that there are typically many sort of common mechanisms that occur frequently within particularly the types of analysis that we see at Sandia. So for example, a fastener or bolt can occur multiple times, can occur maybe even hundreds of times in an assembly. And if we really want to represent those in an accurate way, there's often, first of all, we need to identify where those are. And then secondly, once we know where they are, can we prepare them for analysis? It's typical that you cannot use the geometry that a designer has given you directly in an analysis for a fastener, for example. it has to be represented in some way that the analysis code can utilize. So sometimes it is anywhere from just a simple contact surface that's represented between two adjoining volumes, or it could be a sort of a simplified representation of the fastener. But it's in this case, it's very analysis specific. And depending on what the requirements are for your particular analysis, there may be different requirements for reducing that for your simulation. So what we'll do to begin with is look at this classification problem, which is, it's really just a kind of a shape recognition problem. But most of us are aware of the AI in our iPhones. It's able to recognize a face, or it's able to recognize some shape as a dog or a cat, or as a Matt or a Steve. So in a similar way, we are able to recognize particular shapes within a CAD environment to be able to say that looks like a bolt, or that looks like a washer. But that requires training data. So just like you have to provide examples of pictures of Steve or pictures of Matt, and the more images you have, the more likely it's able to do that classification correctly. So this little schematic kind of shows you the approach that we're taking. So on the top left-hand side here, where we take a CAD model, once you've imported your training data, you're able to just simply hit the analyze button. It'll go through and compute or do a prediction on each of the parts that are within your design solid model, and it'll just give you a list. So here we've got a list of bolts, gears, pins, springs, and then you're able to expand that, zoom into specific, in this case, bolts. And what we have to date, since bolts seems to be or fasteners seems to be a particular topic that is, for our analysts at Sandia, takes a significant amount of time. We've kind of focused on that to begin with. And so what we have is this a series of dialogue panels where the user is able to sort of customize the result of their bolt in this case. So it's kind of a recipe that says, okay, now let's take this bolt and reduce it in a particular way. So it could be anywhere from just doing this simple reduce operation all the way to, you can mesh it, assign boundary conditions. You can provide some information around this is called a core. So right surrounding the fastener, you may want to incorporate or really sort of zoom into the details of that. If you're looking at things like failure conditions around a fastener, you may want to have additional resolution surrounding that. So allowing you to do some of that, sort of coring out some additional information there. So that's sort of the gist of it. So the idea would be to say, okay, give me all of the fasteners as quickly as you can. I'm going to do a little bit of trial and error to figure out, okay, I want to reduce it in this manner, and then take a dozen, 50, 100 bolts, and then reduce them all at the same time, rather than having to do those one at a time. And in the past, what would happen is a user would have to go through each one of those individually and figure out and sort of repeat that process over and over again on each of those fasteners. So let's do some real Cubit stuff here now. So I'm starting off with Coreform Cubit here, and we mentioned this last time, but there is a power tool over here. So typically you'll come up with this command panel. You'll see your command panels, which basically define all of your the hierarchy of commands that are in Cubit. We're going to be using these power tools over here primarily, and if you click, so it would be the second one over here. So the first one is usually this wizard tool. The second one is the geometry power tool. Other tools are for meshing, others for mesh quality, for example. We're going to focus on the geometry diagnostic tool here. So the first thing you want to do is do this options. And so I don't have anything read in here at this point, but basically this will kind of set us up to do this part classification. So typically what's going to happen, you will see something like this, okay, if without having loaded the machine learning models. So without machine learning, you will have some diagnostics that you can use that just use some geometric reasoning to be able to identify specific types of diagnostics within the geometry. For example, where are the small features? Where are my bad angles? Where are my holes? We're not so interested in that in this case. As soon as we hit this load ML models, it will load our machine learning models, and it will give us some additional diagnostics. So the one we focused on last time was this TETMesh for quality metrics, and that provided us some training data to allow us to predict meshing outcomes. So we're not going to do that this time. Instead, we are going to focus on part classification. So there are two different categories for part classification. One is for surface classification. This one is more of experimental at this point. So you are able to do identify specific surfaces within an assembly. We're not going to look at that one this time. We're going to focus on part classification. And so these are all of the different categories that are predefined for us. We'll look at how we can define your own in a moment here, but basically these are the ones you get for free. Okay, and I spoke to some of our analysts. These are the types of mechanisms that they were interested in, and so we kind of started with those. And so what happens is when Cubit ships now, where you will now get training data which is packaged with Cubit, and as soon as you do this load ML models, it brings in that training data, so you're ready to do this part classification. So that's really the only setup you need to do for this. So let's actually do a real simple model just to give you a sense of what we can do here. So we'll start with this this little bolt configuration here. So in this case, we would like to, so it's pretty simple. We can see that there's two bolts here, but just to give you a sense of how to use this tool, you can define which volumes you want to analyze. So most cases, you just want to do all. And then if we do an analyze now, it quickly went through, and now it gives me two lists. Apologize, it's a little small, but you should be able to see a list of two bolts, and then other category is just the other volumes there. So similar to the other diagnostics, you can do similar things. So you can click on a volume, you can draw it, you can zoom to it, you can do things like draw nearby volume, so you're drawing the bolt with its nearby volume. So that's useful if you've got really complex assembly, you just want to sort of narrow down the bolt with its surrounding volumes. Okay, so that's sort of in its simplest form, that's all the classification is. It just says here's a list of your parts. But what actually makes it useful in this case is this little show solutions button right here up on the right at the top here. When that occurs, that will make this window appear at the lower right here. And what this gives you is a series of tools. So they're sort of predefined tools that you can utilize. You'll always get this delete option, but you will also get a number of different options here. So for example, let's take the first one here after the delete. If I right click and say preview bolt, it will draw the surrounding volumes with a red wireframe and then Similar to the other preview options in Cubit, it will give you a blue version of that. So if I do a refresh display here, let's just so that we can kind of see what's happening there. You can see that the bolt, there's a hole, there's this sort of conical thing at the end, and the bolt is actually overlapping, which is pretty typical. You know, sometimes you may have threads, you may have lots of different details in there that you just don't want. So when we did that simplify, you notice that it got rid of all that information. There are some other tools. So let's just, so that we can kind of see, let's use this spider option. So if I do a preview reduce bolt now, what you'll see here is that the bolt is removed, and in place of that is a series of finite element edges. And so with what's called a rebar element right at the center. So this is a typical way of representing fasteners. So rather than having the fastener itself as the geometry, it's represented as a series of edges. So again, it's really analysis specific. You'll have to sort of look at what your analysis code will permit. There's a couple of different flavors of this one as well. So if I can do a reduce bolt here, you know, rather than, you know, this sort of spidering option, you'll have these sort of wagon wheel type configuration there. A couple of others, you can do this core option. So that will core out the surrounding geometry so you can mesh that separately. Okay, so we haven't actually done anything at this point. We're just doing previews. So if I do a refresh display, I haven't actually done anything. So if similar to the other diagnostics, I can go in here and go directly to a panel over here, which will allow me to do additional or sort of customize my command. Or I can just simply, if I like what it is, I can double click on it and it will actually execute that for me. So now it's showing me, because it's actually green now, it shows me that I've actually changed the geometry at this point. It's just showing me the wireframe at this point, but if I do a refresh display, it shows me what's happened there. And of course, I can always do an undo if I don't like what it did there. So let's look at some other things here. So I'm going to do an analyze again. After you've done an undo, sometimes you do need to do an analyze again. So I'm going to click on both of these volumes, and let's say I want to actually perform the same operation on both of those. So if I right click with both of those selected now and choose the flavor that I want. So let's do this reduce bolt and fit operation. So it populates that with these two volumes here. We can also use what's called an insert. So sometimes there's an additional volume surrounding that shaft that you can utilize as well in there. But here's sort of what I mean by the recipe here. So you can go through and choose multiple different options here. So for example, I can remove this key cavity. So this sort of hex region in here. You can do things like aligning the bolt to the hole. So if there's a slight deviation, perhaps the analyst didn't quite make the fastener exactly aligned with the hole, you can do things like just align it for me. You can match the hole to the diameter. In this case, we're going to do a tight fit so that we're going to get rid of the hole, and then we're going to fit the fastener to the hole. And we can do things like web cutting as well. So often you will want to change the block type, because it may have different material properties based on that, whether it's the head or the shank or the plug. So I'll show you how that works as well. And then you can also do things like hex meshing it, and you can define a size. Here that default button gives me a size. Usually it's a little small for me, so I'm going to bump that up a bit. And you can automatically assign blocks as well. So You can name the blocks. You can define the resulting IDs. So let's start with a preview here. So if I do a preview, it shows me this is what they will look like. If I like that, then I can go ahead and do an apply. And so notice here, within a brief period of time here, it simplified the bolt, it cut them, it meshed them, and it created blocks for me. So if I look over here on the left-hand side, it's got 3 blocks now. One is the head block, one is the shank block, and one is the plug block. So within your simulation code now, you can utilize that that information for the block information to quickly define those. Okay, so that's sort of the basic approach here. And just to show you, we do more than just simple two volume problems here. Let's do something a little more interesting. So let's start with this gondola vase problem here. Again, if you're interested in reproducing these, I think, Matt, you may have these on your site, but I know that Sandia certainly has those on the Cubit Sandia site. If you can download the Cubit100.zip or Cubit200.zip. These ones are in the Cubit200. All of the slides and the models as well, if you want to play with these.
Those are on the Coreform site. Yeah, thanks, Steve.
Okay, good. Okay, so this one is a little more complicated. I'm going to turn off my my transparency here. So this one has a bunch of bolts we can see pretty quickly. So just to let you know, there's nothing to say you can't use some of the existing tools that in conjunction with the classification. So if I pick a bolt here that I want to use, if I right click here and say select similar, it will find all of the bolts that are the same, and you can use that as your mechanism for, just by visualizing it. Classification is just another way to do that selection process. So let's go over here and do this. So we've already got our part classification defined, so no need to do that again. If we do an analyze now, so what this is doing now, in this case, there's 128 volumes, and so it takes a little longer, but it goes through and computes the category for each of those volumes. So in this case, it found 48 bolts. Each of them are named here, and we can zoom into each one of these. Well, actually, let's just start and look at the all of the bolts that we have. So there's our 48 bolts. Just so we can see what else we have here. If we do a draw all add, we can see an insert is really just sort of this cylindrical thing. It's in context. These are probably not inserts, but that's sort of what an insert looks like. It should be something that is surrounding a shaft of a bolt, but it's really just this cylindrical object. I think there's a few nuts here. Yeah, so you can see those right there. And there's a few washers. Yeah, again, a washer is a sort of this flat annulus. So it doesn't know its context. It says, well, that sort of looks like a washer. But in this case, no, it's not really a washer, but it certainly looks like it. But these are more likely washers over here where it added them here. Okay, so let's look at a quick example here. So I've got my 48 bolts. Let's draw all of those. I can let's zoom into one of these. Let's just start with the first one here. Okay, so we got that one here, and it's part of a series here. So I could start with this. I could select all of those that kind of look the same up here, or I could just simply go, once it's found it, I can say select my similar volumes, and you'll see that it selects them over here on the right hand side. I'm going to draw my nearby volumes here, so you can kind of see it in context. And I'm going to go directly to my reduce bolt and fit option right here. And in fact, yeah, this is an issue. These are not insert volumes. I think I've resolved that in the later version. So we're only looking at bolt volumes here, and we can do some of the same things we did before. So we can remove the key cavity. Let's do like a tight fit. We can do a web cut. We can mesh it. We'll find out what that size is. Let's make that a little bigger. And we can assign some blocks. And if we want, we can do a preview. And obviously it takes a little longer because it's got the 8 bolts that it's dealing with. You can see it in context. And if we like what we see here, we can go ahead and do the apply. And you can see we've done those pretty quickly. Okay, so there's our 8 bolts, and there's the heads that are combined into a single block, the shanks, and the plugs, which are in the lower volume there. Okay, so that's sort of a use case that you might want to use it for. So let's look at something that's maybe a little more complicated now. So let's do this assemblage2.stat file. Okay, so here's our model here, and just so we can see it. Yeah, so this has got lots of sort of interesting things going on the interior, but there's a lot of things that kind of look like bolts in here. And so let's just go ahead and use our classification tool again. If we do an analyze here, this one has 123 entities. And this one now says, oh, you have 79 bolts here. So let's do this draw all. Let's turn this off just so we can do some visualization. Okay, so how did it decide that all of these are bolts? Well, that's really a result of me going through and defining, going through and creating training data and deciding that, this is a bolt, but so is this, and so is this. And so it may be that you want to break these up so that perhaps you don't want to define this as a bolt, or you want to define this as a pin, or you want to do something different than what it's actually defined here. So how do we know if something is how confident are we that something is a bolt and something may not be? So what you'll see here over on the right-hand side is this confidence value. And as we start to go down here, we'll get to a point where they're no longer 1.0. 1.0 says, yes, I'm 100% confident that that is a bolt. So if I zoom to that thing here, it says, yep, that's a bolt, because I have likely provided some training data that says anytime you see something that looks like this, we're going to define that as a bolt. But as we go down the list here, let's actually look at the one that's all the way down to here. It says, well, you're a bolt too, but it's not quite as confident. It gives you a value of 0.5175. We may not want that. So how do we change that, or how do we define our own training data? So in this case, we can use the command line tools to do that. So there's a series of command line tools, and I'll give you a quick, here, let's go down to, I think it was right here. So there is a series of command line tools that allow you to manipulate these. So there's this classify command, and basically you classify it, give it the volume, and then you can either define new training data, or find information about the classification itself. So let's use this confidence value here, and I'll show you what that means here. So if I'm doing this one here, that's volume 83. By the way, if you have something selected and you hit the E key, it will echo that down on the command line here. So I do classify volume 83. That by itself, currently there's some debug information that's listed here, but really what we're looking for is this information right here. It says volume 83 is a bolt. If I add this additional keyword here, confidence, it will give me a list of all of the different categories, and it says here's my confidence. So bolt, it says it's a 0.517. A pin, it says it could be a pin, but bolt wins out, but not by much. So if I really want to make this a pin, I could say do the same thing I did previously, but now we can say, hey, make that a pin. So basically what that just did there is that it went out and computed the what we call features of this object, added to my training data, and then rebuilt my training data, and now we have a new set of training data with that additional model changed. So now if I do classify volume 83, it should tell me pin, and let's look at that confidence value now. Okay, so it's changed enough so that the pin wins out. So why didn't it become a 1.0? Well, it's because I have a lot of training data that's already there. And so basically you can think of it as a high dimensional surface that we're fitting. And we just added one additional point or changed a point on that high dimensional surface. So it's still kind of an interpolation of that surface. But what happens now is that we've added some additional information to say, okay, now anytime you see something that looks like this, we're going to classify that as a pin. So there's some other things here as well. So let's look at this guy right here. So this one, if we do volume 122 here, it says it's a bolt. And so let's look at the confidence here. Okay, in this case, it says you're a 1.0 here. So I have a bunch of training data that says anytime you see something that looks like this, it's got to be a bolt, but I don't want it to be a bolt. So in this case, I'm going to, I want to remove it. It's likely that this volume itself is in the training data itself. So I'm going to use this reclassify command, and I'm going to say volume 122, and then I'm going to add this new category. I don't have a screw category yet, so let's try this. Okay, so now it says it's reclassified, and so let's see what happens now if I do this guy. Okay, so now it's high enough now that it's now classified as a screw, and bolt is just slightly smaller. So I should be able to find the rest of those. So a couple things you can do here. I can go in and do my analyze again here and find everything I want. In fact, let's go ahead and do that. So you'll notice that I don't have screw in here yet. In order to do that, I actually have to unload and load my machine learning model. And as soon as I do that, you'll notice that I've got a screw category in there. And if I do done and then analyze, we're doing a reevaluation of everything there. Let's see what happens here. Okay, so it found one screw. Let's find it. but I know that there's a bunch of other ones here as well. So why didn't it find this one? So it may be that we need, so it has a category of one single example. So it's enough to find itself, but it may not be enough to be general enough. It's sort of like having one picture of Steve. It may not be enough to be able to recognize all of the different pictures of Steve. So we may need to give it some additional information. So if we want, we can go in here and here, let's pick a few other examples here. And if we do that, classify volume, we can do as many volumes as we want, and we can classify those as screw. Okay, and it goes out and adds that. And now let's see what happens here if we do an analyze. If that will give us more information. Okay, so now it gives us 7 screws out of that. So now draw. Okay, so now that's probably closer to what we want. We may have missed a few, but again, the more examples you have, the more likely it's going to find all of the categories that you're interested in. Okay, so what about this training data? Where is it placed? So you get some free training data when you download Cubit, but now you're defining your own training data. So that is persistent. So you don't have to redefine it every time you bring up Cubit, and it is placed in a applications directory on your machine. So if I do this command here, classify list. Okay, so what you'll see here is it shows me all of my categories. The U here says that you have some user training data associated with it. So you notice that, so I had done this thin category previously, so I had some user training data. But notice that I changed the pin category. I also added this screw category. So now I have some of my own user training data. And so basically it combines the user training data and the Cubit training data that's provided. So where is that? So you'll see this little additional information at the bottom here. So the Cubit training data that is loaded when you download Cubit is here. So that's basically in your installation directory here. But there's this additional training data that is in, so I'm on a Mac, so it'll be different for your PC or Linux. It's in this library application support. And so basically you can build this up. And at some point, we don't have a mechanism to do this right now, but we would like to be able to have you share that training data with colleagues or with Coreform or with Sandia, so that we in the future, if we want to have additional categories that are important for our customers, then we can sort of ship that with it. But typically, if there's some proprietary information, and you'll just have that within your company that says, here's my set of training data that I'm going to utilize here. Okay, so in the last few minutes here, I want to show you a couple of other things that you can use with, so you can indeed use this with the Python environment. So if I go to the help here and do Cubit help, okay, and I think all you need here, I think Python API, and we want the Cubit interface namespace here. So I apologize if you haven't used the Python API before, but basically it's the ability to use Python directly within Cubit as a way of querying information about the model. So I'm just going to find, let's see, machine learning. Okay, so there's a category here called machine learning support, and these are all of the various functions you can do. The ones that are probably most useful, there's some kind of detailed stuff. You can utilize this for some of the things that I described last week, to be able to grab the the prediction for mesh quality metric, for example. The simplest way to use this would be things like get the ML classification or get the, let's see, the categories. I think it was, where was it? Yeah, get ML classification categories. So the way you would do that is, let's go into our journal editor right here. And we're going to use Python right here. So you can say something like cat equal, you always use the qubit here. And then so get ML classification categories. And then we're going to get the volume categories. Okay, so if I run that now, and then I should be able to do, let's do a print cat here. Okay, so at the below here, now this gives me a vector that shows me all the categories that I've got here. So I can also, here, where's my, I think there's an issue here. We need to, this sometimes goes behind. I think this is a Mac issue. It sometimes goes behind and I got to go hunt for it. So I can also do, you know, we'll call it my cat is equal to qubit dot get ML classification. And then in this case, you would say, I want the volume, and then give me some, let's see, so that one is volume 39. So just give it a number here. And then I can do print my cat. And let's see what happens there. Okay. I guess I need to spell that right. My cat. I'm going to run that. Okay, so it gives me, it does the classification quickly for you. So why would that be useful to use? Well, you can do things like sort of finding all of the bolts quickly in your model and using some sort of loop, and then using those IDs now to be able to quickly do some sort of reduction on those, or perhaps deleting all the bolts or deleting all the springs or whatever your category is. The other thing you can do, which is useful, is using it with the a new keyword context. So if I did something like draw volume with category. So this is new here. So if you say with category, and then now give it a category that is existing in there. So basically what it will do, so it has to go through, it takes a little bit of time, but it will go through and do, again, the computation to compute the features for all of these, but now it's from the command line, I'm able to draw those quickly. You can also use that to do things like, instead of draw, I could do something like group my bolts add. So what that does is, whoops, let's make sure that's the right thing here. Group my bolts add volume with category bolt. So what that will do is, again, it'll do the computation again, do the categorizations, and it will create a group that has all of the bolts in them. So let's go ahead and do that. It's creating a group called group 6. And okay, so we see that was just created here. So now we can go through, and it's a persistent group now that we can do things with. So I can just say, draw my bolts. Okay, and it'll just do that for you. Okay, so we have about 15 minutes left, and I'm happy to take any questions. And Any comments, questions?
Yeah, thank you very much, Steve. There are a few questions that have come in. One of them is, can you increase the training data by adding noise or perturbation to the existing models?
Yes, you can. So just in the way that I showed you there, if you have examples, then just add whatever you want as examples, and that will be added to your local training data. And the next time you do a classification, it will incorporate that new set of noisy data or whatever you want to call it.
Cool. Thank you. Here's another question. How was the training data labeled, and which machine learning algorithm was used to classify the parts?
Yeah, so in fact, we used what's called a random forest, specifically ensembles of decision trees. So basically what we do there is for each volume, there is a series of, there's a fixed length vector of scalar values that represent any particular volume. So given a volume, we can compute those numbers. So those numbers would be things like what's the volume of the volume, what's the bounding box of the volume, what's the genus, or what's the surface area, or the surface area divided by the volume. So just a series of just scalar values that are used as features, that becomes my training data. And so we utilize some existing tools. And so the tool we chose to use was ensembles of decision trees. We actually have a paper on that if you're interested. I can send that to you, Matt, if people are interested, and we can distribute that. But we're using scikit-learn, which is an open source Python package that is actually included with Cubit now in order to do these predictions. Probably more information than you ever wanted to know, but yeah, there's lots of details there. I could tell you about the machine learning details.
Yeah, no, thanks for your openness, Steve. Appreciate sharing that. There's another question. Does the classification work on all formats of CAD files? Does it work on STL or 3MF format solid geometry?
Yeah, that's a good question. So it is ideal for boundary representations. So if you've got a step file, ACES file, anything that can be imported and create sort of a boundary representation version of the model. So as far as STL, what happens with an STL, if you import the STL as a mesh-based geometry, we are indeed creating a boundary representation from an STL file. So if I imported a gear, for example, as an STL, the boundary representation is defined by a feature angle. So we'll create curves, surfaces, and volumes based on wherever we will insert those vertices and curves where there's an angle. Now we can utilize that information with the classification as well. So yes, you can use it with STL provided you import it as mesh-based geometry.
Oh, interesting. Cool. Another question. In this framework, can a volume have two or more feature identifiers? And how does it deal with features such as manufacturing etchings or recesses into a surface?
Yeah, so in this case, with the volume classification, there may be a difference. So the features, for example, are based on, so one of the features would compute all of the, or the sum of the surface area. So if you have etchings, that may increase the surface area, but probably not by a lot. So as long as you provide an example that has those etchings in it, it should find it. But again, that it's all sort of based on, do I have an example of that? to sort of augment my training data. Again, it's sort of like creating this high dimensional surface. Anytime you add some additional information to it, it just augments that surface to make it more accurate. And if you've got some examples that have etchings in it and you want that to be part of your high dimensional surface, then it'll just do it. Okay, so the short answer is yes. You can use any sort of surface representations, and it should find it as long as you have examples of it.
Great. Steve, thank you again so much for taking the time to share both of these webinars with us and also for making this tool.
You're welcome.
Yeah, so to the Coreform Cubit community, we look forward to seeing how you use this tool as well. We welcome any feedback on our forum or just emailing us directly, and that can influence where this goes from here. So thanks everyone for attending and have a great day.
Okay, thanks, Matt.